Okay, so we've reached now ahead with this section. And now we're actually going to develop and apply some tools for determining the convergence of a sequence. A lot of this is going to feel derived or similar in nature to what we covered in chapter 2, and that's no accident, really. So my suggestion here is to think the usual rules apply. So formally, let's talk about what happens when we have two sequences, A sub n and B sub n, that converge to A and B, respectively. I've always found it weird that in math we do that. Two things do this, two things, respectively. And the connection here is that we don't want to waste too many words on saying the same thing twice, right? A sub n converges to A. B sub n converges to B. And so we use this like parallelism, right? Like a rhetorical strategy to just say, oh yeah, those two converge to those two, respectively. And their respectively is just like a cop-out so that we don't get caught with our, saying something that isn't very accurate or that can be misinterpreted, but that's why we also pick two letters that match, right? Anyway, this is commentary that really has nothing to do with the fact that with what we're going to be talking about, just if you've noticed some patterns in your math courses, right? And then the textbooks that you're using, just be aware that there's deliberate choice here, okay? All right, so here's the first limit law, which is that the limit of A sub n plus B sub n is A plus B. So in other words, the sequence composed of adding the two terms of A sub n and B sub n will converge to A plus B. Similarly, A sub n minus B sub n converges to A minus B. Now, if we have a real number that's not 0, called C, then the sequence C times A sub n will converge to CA. Two other rules that have to do with operations here will apply. Well, three really, but two that are principal. So A sub n times B sub n, the sequence that you get from multiplying the two sequences together term-wise, is going to give you A times B. And similarly, A sub n divided by B sub n is going to give you A divided by B, provided B is not 0. Right? The last two that I want to cover here are the sequence that you get from raising every term to the power p will give you A to that power p, provided we have a positive sequence, right? All of the terms are positive and the power is positive as well. And it can be any power. It can be a fractional power. It can be a whole number power. It could be an irrational power. It doesn't matter. And the very last thing that I want to cover here is the limit as n approaches infinity of the constant sequence C is C, and the limit as n approaches infinity of the sequence N is infinite. It doesn't converge, right? So the sequence that is just 1, 2, 3, that doesn't converge. It diverges. Okay. So with this, right? With this list of limit laws, we develop everything else. Okay. So from these, we're going to be able to redevelop some of the usual intuition that we have about when a sequence converges. Okay. So let's see a few examples. Okay. Some conventional examples include things like, let's go back to our motivating example. let's talk examples, right? So 1. What is the limit? Or actually, let's actually frame it this way. So determine the convergence or divergence of the remaining length of the Cantor middle third set. So, in other words, remember that we were talking about the sequence L sub n equals, that was 2/3 raised to the n power. I think n minus 1 power, actually. So, what is the limit of this sequence? If it exists, right? Otherwise, it could diverge. I claim it doesn't, so my claim is that L sub n approaches 0 as n approaches infinity. So it converges to 0, okay? So, how do we verify this? Well, here's one critical consequence of the limit laws. If r is less than 1, between 0 and 1, then the limit of the sequence r raised to the n power is 0. Okay? So this isn't that hard to see, because what is r sub n? So this is, I guess, inside, right? So why? Well, this is the sequence r squared, r cubed, r to the 4th, ... And specifically for us, in this context, right, we're talking about 1 2/3, 4 9ths, 8 27ths. The next one would be, if we're talking about, what is this, powers of 2, right? 16, 81, 64, no, 32. Oops. 32, and then times 3, I think it's like 273, something like that. Don't quote me on that. I don't know how to math. These are fractions that are getting smaller and smaller and smaller, right? Because r, this ratio, which is 2/3, it's getting closer and closer to 0. Yeah. So, in other words, yeah. The remaining length of this set is literally this limit, 0. So we've taken away all the length from the Cantor middle third set. It is a set that has what we call measure 0. I'm not going to talk about any more about that at this point. Let's see another example. One that's a little bit more digestible. Okay. 2. What is the limit if it exists of the sequence b sub 1 equals 2, b sub n plus 1 equals b sub n over 1 plus b sub n. Okay, we've seen this one before, right? So remember that the explicit formula for b sub n is 2 over 2n minus 1, okay? So does b sub n converge? I claim yes, to 0. Again, odd, isn't it? Okay. So how does this work? So the limit as n approaches infinity of b sub n is the limit as n approaches infinity of 2 over 2n minus 1. And so the important thing here is that combining the limit laws work exactly the way that you would expect, right? You can break it up into just examine what's happening in each part of the limit, right? So what is happening to 2 on the numerator? What's happening to 2n minus 1, the denominator, right? And so really we're thinking about this as breaking this sequence up into some sequence that we've constructed from other sequences, right? The sequence of just 2, the sequence of just 2n minus 1. It works in exactly the same way as it works with functional limits, which is constants will not be touched by the limit, right? Constants will just be constants. And expressions with n blow up, right? So we actually end up with 2 over infinity, so to speak. So I'm gonna put a limit equals because that's not, again, we know that that's not how limits work, right? What we do know is that this will converge to 0, right? Because the limit as you go for the denominator, right? That's a linear sequence in n. Another term for this is arithmetic sequence. Right? There's some really fascinating connections between the world of sequences and what we've already explored, right? But yeah, it makes sense. This sequence doesn't converge, it diverges. So the full sequence converges, right? Okay, let's see some more examples. There's plenty of examples to explore here, right? So 3. Does a sub n with a sub n equal to 3 plus 5n squared over 1 plus n converge? Okay, so remember, we've seen that we can redeploy some of the techniques that we learned in a previous chapter in Stewart to being able to figure out whether this sequence diverges or converges, right? So remember, it only converges if it converges to a real number, right? If it blows up to infinity, it diverges. Right? Now, notice that the degree of the numerator is 2 as a polynomial of n, and the degree of the denominator as a polynomial nn is 1. So, in other words, if we're thinking about this as a behavior of rational functions, if we're thinking about the dominance theory, right? A fraction of two functions, which one's going to dominate over the other? The numerator is going to dominate, right? It grows faster as n goes to infinity. So a sub n diverges. If we were to match this to our notion of the function 3 plus 5x squared over 1 plus x, we know that that would have no horizontal asymptote, right? Okay, 4. For what values of p does the sequence a sub n equals 1 over p ln of n converge? Oh, sorry, np. Actually, I'm going to change this up because I realized that this is going to be more interesting. So we're interested in finding the values of p that give us a convergence sequence here, right? So let's think about what this looks like. So there's a dominance theory here, right? So think about how fast do NP and ln of n grow, right? So we know that all powers of n greater than 1, all fractional powers of n are going to eventually grow faster than ln of n, right? So for p greater than 1, right, NP is at least linear, right? Linear grows faster than ln of n, so diverges. That's our conclusion. For 0 between p and 1, right? So we have a fractional power. So think square root, right? Square root of n. That is still at least logarithmic. What I mean by at least here is they're still going to grow faster than a logarithm eventually, right? Diverges. For p less than 0, right? And then now we flip it into the denominator, and now the sequence converges. That's it. Fascinating, right? Okay, one more example that I want to cover here that I think is worthwhile. So let's see, if that was 4, then this one's 5. Determine convergence of Cn equals 2n minus 1 factorial over 2n plus 1 factorial. Okay, so the key part about the factorial operation here is that each factorial can be broken down up to a factorial for a number below it. So in other words, because k factorial is k times k minus 1 times k minus 2 dot 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 all the way down to 3 times 2 times 1, you can choose some point at which you want to just wrap up part of that to just k times k minus 1 times k minus 2 factorial, right? And that's going to be super helpful for when, if we have, instead of k, for instance, right, we're going to have 2n plus 1 factorial. Or it can be written as 2n factorial. No, sorry, not 2n factorial. 2n plus 1, sorry, plus 1 times 2n times 2n minus 1 factorial. Okay? This is the exact same thing that I've written except for the specific case where we're looking at 2n plus 1. So all that is saying is that 2n minus 1 factorial over 2n plus 1 factorial can be written as 2n minus 1 factorial over 2n plus 1 times 2n times 2n minus 1 factorial, and these will cancel out. What we're left with is 1 over 2n plus 1, 2n. I don't need to convince you, or I don't think I need to take too much time to convince you that this sequence does converge, and it converges to 0. Okay. So in the next video, we're going to talk about a very interesting and very powerful result called the monotonic sequence theorem. It goes by other names, including the monotone convergence theorem. In my notes, I started calling it that, but I think I fixed it enough times that it won't be an issue. So in that video, we'll talk about what it says. We'll see some examples, and then we'll see, and this part is completely optional, we'll see the underlying proof of that result. And it's actually very, very deep. It is showing some very interesting and very important ideas. So it's crazy. We'll have plenty of fun with that. But the powerful or the helpful part about it is that it tells you when a sequence converges without having to find the limit of that sequence. And that's a super helpful result. It sets the tone actually for the entire rest of the chapter because, as we'll see, sequences are actually much easier to deal with than series. All right, so that's that for that.